Not working. All right. Okay, so it's working now. I don't know. I don't know what. Okay, great. So sorry about that. Let's start. I'm gonna switch color into red. All right, great. So as I was saying, I'm going to be discussing the attention mechanism. So we can go here. Chapter 10. So remember, we've talked about the entire GPT. I'm going deep into the decoder layer, and inside the decoder layer, I'm going into the multi-head attention, right? So that's really all we're going to talk about. I said last week that we create this 40 by 40 matrix, and I just want to give you this intuition so you can see it's actually not, it's very interesting, but not that complex to understand. So we create something like that, 40 by 40, and you know, it would be, right? And that's basically the attention mechanism where you pay attention to the tokens. That makes sense, right? That's what the neural network needs to learn. What you need to understand is that these are weights in a neural net, but it's also a matrix multiplication. So a matrix multiplication is a neural net. A neural net is a matrix multiplication. This is the insight that's really important, okay? So I will go over this new Jupyter notebook that I added on the linear algebra operations, where basically I'll break down all of these, but this time around, I'll just use random data just to show you the operations, and we're just going to look at the shapes. Now, I want to stress that the function that I'm going to be focusing on is the head function. This one, the init part, and then the forward in particular, where everything happened. If you remember, this is literally this WEI way is the attention matrix, okay, or the scores matrix. Got it? So this is what we're going to do. All right, so let's switch back to the whiteboard. Okay. Okay, perfect. All right, so what I'm going to give you is just a little bit of background on linear algebra. Just, you know, we don't, you know, linear algebra is a huge course with lots of topics. We really just need a set of a few operations. That's it, right? And it's just a mechanical operation. You just have to, like, literally when you do linear algebra, you just learn how to mechanically do it. That's literally it. All right, and that's kind of what I'll do really quickly. I'll show you just a few operations because they are important. And then I'll show you how they are connected to a neural net, right? And that's kind of the intuition. And then this is not really the attention mechanism. This is just like a little bit of background. And then we're going to get into everything in that head class of how the attention works. Does that make sense, guys? Any questions? All right. So basically, I'll just, you know, dive into it. So imagine, you know, this is, you know, very basic operation on vectors, right? So I have a function that takes v, right? So we define this function as being 1, 2 plus v. What is v? V is going to be some random vector, right? So basically, we're just going to start at adding things up, okay? So what I can do is then I call my function f, and now I'm going to give it the vector 4, 4. So in these operations, you know, you have 1, 2, and then plus 4, 4, right? They need to always have the same dimensions. That's really the key and the trick. So if we perform this operation, this would be basically equivalent to 1 plus 4, comma, and then 2 plus 4. And so that should give us what? 1 plus 4 is 5, comma, 2 plus 4 is 6. And that's basically vector operation, right? So you mechanically know how to do these operations, but they're very efficient, right? And this is how we're able to parallelize everything that we do. Make sense? All right, so I did this example basically just to kind of start somewhere. Now, this operation is a little bit more important because this is really what's happening a lot of the time in neural networks, and it just maybe we lose sight of this idea. And so I want to stress that this is really important. This is why I don't like things like keras and so on, because it makes it more available, but you kind of lose touch of what's going on. All right, so let's imagine we have the following. We have something like x, right? And that's, some vector here, 1 and 3. Okay, this would be equivalent to thinking of this as the weights, for instance. Okay, and then we have something else, A here, and that's going to be an actual matrix that is 2 minus 1, 1, 1. You see, they're like a matrix and a vector, basically. Okay, so now I'm going to define this operation, y equal A times x. Now, this multiplication is a matrix multiplication. So it's got a way that it has to be done. The dimensions need to line up, etc. Okay, this is really important. If you look, this looks awfully like the common w times x, correct? And then there's the plus b. And that's the standard neural network. So at the end of the day, the standard neural network has this matrix multiplication, w times x, same as this a times x here. You guys see that? So this is the operation I'm going to do just to mechanically show you how it works, okay? And we're just building up this little bit of background so that we can understand. What we want to understand is the attention mechanism, but it's got a lot of these in attention, right? So that part I'll do in NumPy or PyTorch with a Jupyter, but this part I wanted to do by hand just to show you, because you do this by hand in school. All right, so here then, I'm going to proceed and perform this operation. So you do 2 minus 1, 1, 1, right? That's the matrix. And then you have 1, 3. All right, so now this will be equal to 5, 2. That's the answer that you get. All right, so when you do this in school, you learn that you do this. This is kind of like you do this in school. It's you mechanically by hand align things. So you develop this muscle memory of going, okay, I know how to do it, right? And so this is basically what you do. So what that means is you take 2 and 1, that's me doing this, and multiply it times the other one, which is 1 and 3. And that results in just one value, which is the one that you plug in there. You see that? Then you do the same thing with the other one, minus 1 and 1 and 3, and that gives you the other one. So I do then minus 1 and then 1, 3, those, and become 2. Do you see that? That's the mechanical operation. This is something you just learn how to do. It's a mechanical thing. Now I'm going to work it out. Okay, so I'm going to go to a new page here. So what I want to do is I want to multiply 2 minus 1, 1, 1, and then 1 and 3. All right, so this is the operation that happens all the time in neural networks. Okay, this is literally why we use GPUs, because GPUs were made perfectly to do this. Okay, this is the one thing they do. So the way that it works now is, so I'm going to do the first one, the 2, 1, 1, 3, right? So that operation is actually means that I multiply this 2 times this 1. So that's going to be 2, 1 like that. And then you do plus, and then 1 times 3. You see? So that's the trick. So here I do 1, 3. And that basically will give me the top value. Okay? Then I do the same for the bottom one. So the minus 1, 1, 3. So I'm going to do that here, minus 1, 1, right? And then 1 plus here, and then this is 1 and 3. So I do this minus 1, 1, 1, 3. Okay, so now this won't work on any combination of dimensions. It's got to be the right dimensions. In particular, this has 2, right, in this direction. It's got to have 2 in that direction. And this is a critical thing to understand because this is the trick of how I get the embeddings. All right, so how I can go, you know, from having just 1 to 5, 12, etc. And we'll see that in a second. Okay, this is, you know, very nice. All right, so now to finish this up, then this would be 2 times 1 is 2. Oh, let me do this. 2 times 1 is 2, and then 1 times 3 is 3, right? And I'm going to close this one, and then minus 1 times 1 is minus 1, and the other one is 1 times 3 is 3 plus. So then this becomes 2 plus 3 is 5, and this is 2, basically. If we look back, 5 and 2, 5 and 2. Do you see that? This is just an operation that exists, the mechanical operation. Whenever you see PyTorch.mapMul, that's it. That's what you're doing, okay? And that's what the GPU does very efficient, okay? So I wanted to give you this bit of background, right, to understand this operation, first of all. The next thing we're going to look at is this idea of something called the transpose. So the transpose is this idea. You see that in the attention mechanism. It's there. And it's just a way of like rotating the data in a sense. Why do we need to rotate it? Because we need to perform this operation of align dimensions. Okay, so that's the next thing I'm going to do here. Just with numbers, I'm going to take some matrix. 1, 2, 3, 4, 5, 6, right? And you do this thing called the transpose. It just means shifting it, right? Oh, yeah, sorry. All right. Yeah, so I have the transpose here. So basically what that means is I'm going to take 1 and 2 from row to column. 3 and 4 from row to column. 5 and 6 from row to column. That's it. You just do that. That's just how it works. That's, you know, I'm sure there's a derivation that's like 300 pages long of why that works. I'm not going to do that. Take a math course for that. But just trust that the procedure does work, right? So now this would become 1 and 2, 1 and 2, 3 and 4, and 5 and 6. Okay. Transposed. That's it. That's the operation. You're just moving it. All right. So these are just a couple of things that you needed to sort of have some starting point and background. Now, the next thing I'm going to do is really important, right? I'm going to create a neural network and I'm going to tie that to a matrix multiplication so that you can see that you'd think of a neural network and that's a, you know, linear algebra multiplications, but also you can say, well, if I think of these linear algebra multiplications, what does that neural network look like? You see what I'm saying? You can use it in reverse, and that works really nicely. So for this one, I'm going to use something that you guys are probably very familiar with, the Iris dataset. So if you remember, Iris has 4 features, and it has 3 columns, right? So 3 outputs. So that's the neural network that I'm going to build here. And then I'm going to tie that to basically a couple of important things. All right, so let me draw the neural net first. Okay, so this neural net has the 4 neurons, right? That's the input layer, which means this is X, okay? Then I'm going to create a some hidden layer. Okay, so I'm going to call this one H1, right? This is going to have 6 neurons. Why 6 neurons? Because I decided that I wanted 6 neurons. But this could be 512, 128, any kind of embedding that you decide to do. And that's the beauty of this. You can define this very easily, arbitrarily, actually, and it works, okay? And then I'm going to have the output layer, which is this one, and this is going to be 3 neurons, basically. One hot encoded output for our neural network. So this is going to be the output. Also, I'm going to refer to this as Y. Now, what's important here, this is going to be a fully connected network. So that means neurons from one layer are connected to all the layers in the next one, right? And I'm going to do this for all. So connected, let me know if I miss one. Okay, and then I'm gonna do that one, to that one, to that one, to that one, that one, and finally that one, that one, that one, that one, that one. So that definitely looks like a neural network, right? What we learn, oh, it's a neural network, you know, very fancy, neurons connected by these things. But really, this is just a matrix multiplication. Okay, that's what I'm trying to say. So I'm going to call this one W0 to indicate that those are the weights that connect the input layer to the next layer. Okay, and then this would be W1. I'm not going to make the connection there because it would take me a long time, but imagine that it's right there. Okay. So now, what is this exactly? If we have this formulation as a neural network diagram, what is this in functions? Well, in functions, this would be basically, we call this one W1, right? So I will start from X. So X, the input, times W0, right? So if I take this X times this W0, then I get the next one. So that's going to be H1, and there's always this plus B. B0 in this case, which is the bias. Okay, and that's just adding. You only add, the way that I usually tell students is just imagine that's it. That is what is happening there. You're adding only to the outputs. Okay, the dimensions need to be reflect that. Now, once I've created the H1, to get to Y, it's basically just W1, which is now this set of weights, right? Multiplied times what? H1, right? That's really important. We're moving along. I created a layer, and then another layer, and then another layer, and I'm connecting them. And this is going to be just conveniently B1. This is really the functions. That's the neural network. Remember, we're coming from this one. We're coming from this one. What's important here is that this is a matrix multiplication. So really, now we can imagine what this looks like, right? W0. So I want to now picture what this one looks like. W0, so I can basically do something like that. And I'm going to create a matrix. Okay. So this matrix is going to have X1, X2, X3, X4. Okay. So if you notice, it's just a matrix of dimensions, and we know the dimensions, and this is the part that's really important. Okay, so how many weights do we have? We have, how many neurons do we have? We have 6. So I'm just going to say, because it's W0, I'm going to say W0 and then 0 for the first one. Okay, so that's for the first one. Okay. Then I'm going to say W01, W02, W03, W04, and one more, W05. Okay. Let me, like that. I'm going to close this matrix over here. Okay. And I want to draw this whole thing. Because it's really important, I think, to make this connection, okay? Because when we look at code, all we see is this, right? Matrices with dimensions, multiplications, and you're like, but really, it's a neural network, right? Such as this one. So we define the dimensions. We know that there's 4 here, right? 4. And we know there's 6 over here because you defined it, okay? So these weights are the thing that we can initialize randomly. But as we are learning, right, we're going to learn these weights. That's the whole train, process. We're going to learn these values, but initially we can define the dimensions of it, everything, all the connections, and the neural net learns these weights, okay? Make sense? All right, so now I want to show you something really the next step, right? So we've drawn this W0. So now we can go over here. Okay. And imagine I'm talking about Iris. So you guys remember that Iris has how many samples? 150 samples, right? We've always discussed that. And it's got 4 features. Do you guys see that? And we are going to multiply it, matrix multiply it, times W0, right? And this should produce for us still 150 samples. But the trick is the output is 6. So we literally took the samples that were of 4 features and moved them to the next layer to now be an embedding of size 6. You see that? Another representation. You can think of it as an understanding of the neural network of what this looks like. Do you see that? What those values are, we don't know. We selected 6 arbitrarily. I could have picked 16, 25, 30, 128. The neural net will learn what is appropriate to go in there. Okay? And we define, so the trick is, I showed you before, right? I can do these matrix multiplications. So the trick is, I know what this size is, and I definitely know what I want out here. So the question is, what does this need to be in dimensions in order to achieve that? Do you guys see that? That's the whole trick of this. So this is how you define neural networks. You think of how many layers you want, and then basically you get something like that. All right, any questions so far, guys? Pretty easy, right? All right, so now let's take a look at, all right, so we're gonna do that now with this. Okay, so I'm gonna take that approach. So let's imagine, so now let's think of W0, right, as a matrix that is 4 by 6. Okay, 4 by 6. That's W0. Why? Well, I have Iris, right? 150 samples. What does this translate in the code of GPT? This 150 is basically the batch. All right, batch, so N. So I think we were doing 32, for instance, right? So we do batches of 32 or whatever it is, 64. That's what this is, N. I just used 150 to make it more concrete because you guys probably know Iris really well. So I have this one over here, and this is of size 4, right? Because this is the Iris data set. So hopefully you guys agree. Now what I want over here, oh, sorry, this should be matrix multiplication as we defined it. All right, and over here, I definitely want 156, right? The embedding. So the question is, I know that I'm going to do this, right? So I just need to figure out what the dimensions of this are going to be. So I have this example here. So I'm going to say 4, 6. You see, I define that. So why do I need that? Because this has 4. This vector is a vector of 4. And this vector is a vector of 4. So I can do this. You see that? And when I do this operation, I'm going to produce the first one over here. So let me use a different color now. So what I'm saying is I do this matrix multiplication with this one. They're both of size 4. And I therefore produce the value that goes there. Effectively, I created the value in the embedding. And I want 6 embeddings, right? So then all I have to, if I want 6, what do I have to do here? Just make this 3, 4, 5, 6. Do you see that? So 1, 2, 3, 4, 5, 6. If I wanted 128 embeddings, then this would be 4 by 128. Do you guys see that? See the trick? This is the trick that is happening for you to take any input and map it into another in the next layer, basically. Okay, so that's what the attention does, like everywhere. It's like this thing is going on, but it's basically this. I'm going to take another color here. Let's say green. All right, so now I'm going to do this same one, right? But times this one. They're both 4, right? And that then produces the value that goes there. So I'm going to now switch back to red. And so here you would have your 6 values. So effectively, you created the embedding of the next dimension. And you're going to have that you had 150, 150 by 4. Now you have 150 by 6 just by doing this operation. So this is why you think of these dimensions and basically there's a matrix multiplication there. The trick is that you don't know what these values are initially. You just set like this input and that weight matrix and this output, right? You set the dimensions, you know the operation, and then you force the neural network to go through it, predict. If it's a bad prediction, adjust the weights. Go through it, predict, adjust the weights. You're forcing it to always follow this architecture, this operation, until the weights start to produce good results. You see that because you're using gradient descent. So you set the dimensions. These values are random, but they're the weights that are being updated. Why? Because when we do neural networks, we know that we are updating these weights, correct? And we established these weights are these W matrices. And now, so the trick is, doing that operation, but we define the dimensions in order to achieve the objective that we want to have as an output. Any questions on that idea? Does that make sense, guys? All right, so hopefully that makes sense. So here, I have my 150 by 6, okay? 150 by 6. All right, so that basically is the background that I wanted to give you. And now we're going to jump into unless there's questions or something that didn't make sense. I think the most important thing is this, okay? This concept needs to be clearly understood, right? That architecture means this. Matrix multiplications, you know what you want your output to be, you know what your input is, figure out the dimensions here, know the operation you're doing, you're good. You set the architecture and then let the neural net learn by doing back propagation and all. Okay. All right. So this is the background. Now let's go and break down the attention mechanism. Okay. So I don't need the whiteboard anymore. So I'm going to hit stop here. And I'm going to share screen. All right. So now going back to this. So attention is basically established in this forward function. So if you remember, I said this is where we actually create the 40 by 40, right? What is the 40 by 40? Is this diagram, this awesome diagram that I have here. So basically you're paying attention to the words. That's your objective. So how do you do this, right? And you're going to do this through matrix multiplications. Now, we don't know what the values of that will be. We just set this multiplication and this multiplication will give us this. But then as we go forward and back prop, it's filled in correctly so that eventually we have a model where the loss went down, right? Yeah. Okay. So what I'm going to do now is I'm going to open up Anaconda and I'm going to go over the code to go over the attention mechanism with random data, just the operation. So you can, if you want to look at this function, look at it here. The other thing is I'm not going to use nn.linear. That's the other trick. Instead, I'm going to use what nn linear is inside. Okay, so nn linear is w times x plus b. That's what it is inside. This is how it used to be. TensorFlow 1, when it came out, there was no linear. But they've abstracted it. So, but inside, that's what it is. So I'm not going to use the linear. I'm just going to use the actual equation, okay? So let's go ahead and start our Jupyter notebook. So I'm going to go here. Okay. Desktop. Yes. 365. No, sorry, this is 530. Yes. 530. DLA. 2.4. This. Okay. They are. Yeah, so that's the sentence similarity that we did the last time. So I'm going to do this one now. The conda environment is going to be think this is, I'm just going to do this in pure PyTorch, so this should work fine. So conda activate Pi37 530 2020. Okay, and then I'm just going to launch a Jupyter notebook. What? Did I misspell Jupyter notebook or something? No. This is what we've been using, right?
The HF1.
HF1. Okay. Not my day today with technology. All right, so the HF1. Okay, so 537. 19 is HF, right? Okay, great. So I'm just going to use, instead of typing everything, because that would take too much time, I'm going to use the same GitHub, and I'm just kind of go copy the code, but describe it. All right, so that will be, so as I said, I added a link so that you guys can just reference it. So it's this part, the linear algebra operations that make attention work. Okay, so I'm going to click on it. And then we're going to go through pretty much everything. And I think it'll become obvious how it works, right? So let's get started. So I'm going to import just a few libraries. I did this in PyTorch. So, notebook. All right, there we go. Okay, so I'm going to create a new Jupyter. Okay, I'm going to now open the GitHub. Here. I put it in GPTs. There it is. All right, so let's import the libraries. Okay, so I'm going to go here at the libraries first. Hit run. So all we need is torch and then functional, basically. And functional, we really only need it so that I can show you what softmax is doing in that head class. Okay. Otherwise, you could do this in NumPy. I actually thought of doing it in NumPy, but just wanted to be more consistent. So let's remember what attention is, right? So if you look over here, attention converts X into K, Q, and V, okay? And performs detection mechanism by the matrix multiplication between K and Q. Remember, effectively, you are getting the sentence like I showed in the picture, and you're calculating those weights, okay? But initially, you have to set the neural net with matrix multiplication so that it can learn to do that, right? And so let's take a look at that. So the first thing we need is an X, right? So I'm just going to use random data here. So I'm going to define a batch of 32. I'm going to use torch.rand_n, and I'm going to do n by 40 by 512. As you can see, these are the exact same dimensions, right, that I had before, okay? So I'm starting, remember that we're at the heads section already, so we've already gone through the embedding and all of that, right? So I'm just doing head. Make sense? All right, so I'm going to hit run, and you can see I have a matrix that is 32 by 40 by 512. That's my X initially. Notice that all we're going to do is create these K, Q, and V's, right? So everyone will give you these ideas of K is the, Q is the query, and V is the value. It's something, you know, don't even worry about that. Just think of what is happening mechanically in the linear algebra operations. So the linear, everything under Q here is that linear. So nn.linear would do this in one line. I'm breaking down nn.linear into the actual tensors that are W times X plus B, right? That define a linear layer. So I'm going to grab first WQ. There it is, WQ. So notice I'm going to define this to be the weight matrix, okay? Notice this is really important. I'm saying that I want it to be 64 here, okay? So I'm doing that trick where I define how many outputs I want of this matrix, and I want it to be 64. So this is actually like in the, I think I already closed the whiteboard, but the W that I was defining so that I can get the output that I want, okay? So notice this is 32 by 512 by 64, okay? The WQ. Then I need this BQ. Okay, and this is also n by 40 by 64. So hit run. You've got that. Now you're going to bring together everything to perform the operation. So here I'm going to do, you can see that here, the matrix multiplication. I'm going to use the torch.mapMul. In the code, in the head section, this is the @ symbol that you see there. That's a new thing as of like Python 3.6 or yeah, 3. And up, but it's the exact same function as torch mapMul, and I just think it's more clear to use torch mapMul, the matrix multiplication basically. So you can see what is happening here is X times WQ. Do you guys see that? X times WQ, and now I'm going to run it, and you can see that at this point I took X, multiply it times W, and I created Q. What does that mean? I ran it through a neural net, and it's in the next layer. Just like I did iris, right? So X, W, hit in one. That's it. X, W, Q. Okay? That's it. And this is all that's happening in linear, all right? So you're going to transform all these X's into Q's, okay? So now I broke this up into parts. I could have done it in one shot. I'm just going to add the BQ. Remember that the BQ also has to be learned. It's a set of weights, basically. So I take the Q, and I just add the BQ. But what's important here is the shape is still 32 by 40 by 64. You guys see that? So then I repeat the process with K. What is K? It's another thing that you start with X, another set of W's to get that K. That's what they did. So let's go ahead and do that. So you're effectively comparing X to X, but not through X, because you end up comparing K and Q. So it's like X was here, and then you got a next layer, right? That's what you compare, the next layer. Okay, so now I'm going to do K, this one. You can see it's exactly the same thing. I don't instantiate X again, right? I just So I'm not going to instantiate X again because I used the same X as in the code. But I do create a new WK. This is another linear, right? So if we go back to the code, we had another nn.linear for this part. So you can see WK is instantiated. There's the dimensions, okay? Then I'm going to do the same for the bias, so B. That's going to be this BK. Okay, I'm going to run that one. And then, once again, I perform the matrix multiplication. See that? How simple that is, right? So notice here, torch map mul, same X as before, with its own WK to produce K. Print the shape, there it is, 30 by 40 by 64. I'm just going to add the bias. Yeah, I'm going to add the bias over here. Print the shape once again. There it is, 30 by 40 by 64. So that's what you did. You effectively take X, run it, becomes K through a neural net, right? Run X through another neural net, get Q. Now comes the attention mechanism. You have to create that 40 by 40 between these two, K and Q, which are related to X. So it's XX, KQ, and then do the operation to create the score. Remember that we'll have random data, but because it's a matrix multiplication, it's a neural net, so those weights need to be learned, basically. All right, so that's where this attention mechanism comes in. So notice here I have attention is Q times K, and now it should produce N by 40 by 40, the thing where you pay attention. So how do we do that? Take this one over here. Notice that I just, once again, torch map mul, Q times K, except I transpose one of them, right? So that's that transpose operation I showed you before, just so that it'll result in what I need, which is N by 40 by 40. The N should stay because if you have an N of 32, that means you have 32 sentences, correct? That's what that means effectively. 32 input sentences, so you need to pay attention to each, each is individual. Like first sentence, it's 40 by 40. Second sentence, it's 40 by 40, and so on. Right? So that's what I'm doing here. Q times K. And if you notice, there it is. Magically, I've got my attention matrix. That's it. That's all it is. You create this structure of neural network layers by doing these matrix multiplications. Now you can run inputs until the end, predict, compare to the real, back propagate, adjust the weights. Got it? Yeah, that's it. And so the rest is just the mechanics of, they have some very interesting mechanics, but we have achieved here the 40. This is the attention matrix right there, 40 by 40. So now let's keep going. Now we have this V, right? Now there are some operations, like there's a softmax, there's the masking. I'm skipping those for now because I just want to focus on this part of the operation. So notice that then you have a V over here, right? So I'm going to go ahead and also do the V. And notice it's pretty much the same. I run it through a neural net and then .linear, but I'm doing it manually. So I create the WV, N by 512 by 64. Okay, there it is. I'm going to create the bias as well. And by 40 by 64. There it is. And now I'm going to perform, once again, the matrix multiplication. So that I don't directly use X, but I'm instead using the next layer in the neural net. So notice this is X times WV, and that's going to give me V, which is 32 by 40 by 64. I'm going to add the bias. Okay, so there it is. And now I have V. So why is V necessary? Because you took X, converted it into K and Q, multiply them, and you got the attention scores, which is N by 40 by 40. But now you need it. You need what? You need it to go back to n by 40 by 64. See that? That's what it's for. And so now, I mean, I'm pretty sure semantically it means something, but this is the operation. So now we have a V. So there it is. Copy. Control V. Notice I take the attention scores, which if you remember is 32 by 40 by 40. I'm gonna mat mul it with V. 32 by 40 by 64. That's the neural network architecture that you create. And effectively, you can create this attention and everything so that you learn weights based on the relationship, right? It's amazing, but it does it correctly because at the end of the day, it's trying to do what? It's trying to predict really well, right? It gets penalized when it predicts badly. So it effectively, it uses the structure to learn weights that tie one word to the other. It's kind of like this is what you want, and you set this mechanism in order to do that. So now I've run through one attention head. Do you guys agree? I haven't done the softmax or the masking, but I did run through one attention. X went in through an attention, and it is out of the attention mechanism. But remember that our matrices were 32 by 40 by 512. This is 32 by 40 by 64. Do you guys remember why this happened? It was because we have 8 heads, right? We wanted to pay attention to it 8 times. So we compressed it to 64. Now we want to concatenate, right? So that's the next step. So here we're done with one attention. X went through it. So now what we can do is we want to concatenate all 8 heads, okay? So what I did kind of to keep things simple is I didn't, to use the same data, out basically contains one head, right? And so what I did is I just repeated that same head in the list, but obviously this is where the neural net had the mechanism for, because it took the head class, instantiated it 8 times and ran X through it. So you had effectively X going through them. I'm just using the same one for the sake of simplicity. All right, but because I want to show you the concatenate operation. So here you can see I'm going to basically create a list comprehension. So that's going to give me exactly what we had in PyTorch, a list of 8 heads. Right? Only here I'm just using the same one. Okay. And now I'm going to print this out just to show you that there are, in fact, 8 heads that are 32 by 40 by 64. So this would be the output of the neural net, the 8 heads, right? And now what I want to do is I want to concatenate them because I don't need 8 32 by 40 by 64. I need 1 32 by 40 by 512. All right, and that's exactly what I'm going to do here. If you notice, that's pretty much the same command that's in the GPT. So all I do is torch cat, list of heads, the last dimension. Okay, and so now if you notice, once again, 30 by 40 by 512. That's it. You build these network architectures and just remember that their connection to matrix multiplications is very important, okay? But you can manipulate the size of the embeddings, whatever you want, just by thinking of the dimensions of these operations. As long as the multiplication is correct, that's all you need, and then run data through it, evaluate the loss, backpropagate, update the weights. All right, so now we are back at 32 by 40 by 512. So we're almost out of the decoder layer, but there is in there a projection, basically. That's in the code. I think it was actually called self.proj, P-R-O-J. And it's really just an operation, a linear operation, where you take this one, project it to a higher layer, and then back to 512 again. Okay? So that should be in, I guess I should go there. So that's going to be go here. So I want to show you, I guess it's a good idea to show you where we are. So we go back to head. Yeah, this is head, right? So we are basically we went out of one head and we're in the multi-head, right? Multi-head. So this list of heads, right? And then this concat is exactly what I just did. And then that out goes into this proj. And if you notice, proj is just an NN linear. So it's just going through another neural, if you think about it, another hidden layer, and then back to the output. All right, so this part is basically this over here. So 8 times 64 is 512. So then you're going to take another set of weights, W0 in this case. The dimensions have to be correct. There it is. You want to use this as a weights matrix just so that you can get the output that you want. Okay, so I'm going to do the bias. There it is, 30 by 40 by 512. And once again, I'm going to perform my famous, very famous map mul. Okay. No, it's really, this is the most important operation in all this stuff, because it's what the GPU does effectively. All right, so control copy. There it is. So I take outcat. Outcat is the concatenated 8 heads. So the 8 heads are concatenated once again to become the thing. Notice that when you define all of this, you don't know what those values are random, but you define the architecture so that 8 heads are created, then they're concatenated. The weights are populated later as you're training. And you're just forcing the model to run through all of these and find the best set of weights to produce the best set of results. All right, so let's go ahead and perform this operation. So outcat times W0. Notice, right? So n by 40 by 512. It's just projecting to another layer. This could be bigger or smaller if you wanted it. It's, you know, whatever you define here. And then you can add the bias. There it is. So that's basically it. And that's it. So you take the concatenated ones, run it through another layer, and get an output. Does this make sense, guys? That's it. That's attention. That actually this is central, right? So if you understand this and practice it, I would say go back, read up on the lecture, but this is the fundamental concept of neural nets, that they're basically a whole bunch of matrix multiplications, and they, you know, they really, there is that relationship basically. Any questions? That's it. That's kind of what I wanted to cover. And yeah, I missed some of the details, right? Like the softmax and all that. But I don't want to give you too much. I just wanted to give you this, and hopefully that clarifies some things. All right. Yeah, so this definitely concludes transformers. So next time around, next Wednesday when we meet, we have an exam at the second half. And during the first half, I will just go over now fine-tuning Hugging Face examples. Okay, so we'll fine-tune the GPT, the BERT, and maybe a classification task, and then possibly then get into RLHF. Okay, please start working on the RLHF project as much as you can. And I'll work with you guys. That will be the next assignment. Yeah.
So basically, you want us to find model on Hugging Face and use the RL.